All right, guys. So we said we're going to talk a little bit about chemistry. In pretty much any biology book you ever look at, one of the first, at least one, maybe two of the first 4 chapters in the book are going to be a little bit about chemistry. Because you can't really understand how biology works without knowing a little bit about how chemistry works. So you're getting a real fast overview of chemistry here in the next few days. When you get into a real chemistry class, yes. Yeah, it does. Chapter 2, Chemistry of Life. Alright, so you gotta know some stuff about chemistry. When you get into a real chemistry class, which a lot of you, that's where you'll go next, there's a lot of math. In this class, we're not doing much math in our chemistry. We're getting just big ideas. We'll move on from there. But realize that the next step of regular chemistry is going to involve some science plus some math. And that's how most of the sciences from here on up will be. Some science, a lot of math, kind of tied together. We talked yesterday about elements. And we said that elements yesterday are substances that are only made out of what? One kind of atom. And we essentially said that yesterday on Earth, how many different kinds of atoms are there? 100 and something. The number on the periodic table, right? 100. It's 112 up there right now, but that's an older periodic table. It's up to 120 something. Okay.
Why didn't we have to learn so many numbers?
Why?
Yeah.
We're not really learning that many numbers. Not too many in here. Anyway, element is something made of only one kind of atom. We talked a lot about atoms already. We said they're substances, particles, that are the smallest particles that do what? Atoms are the smallest particles of the substance that what? Keep the properties. If you break up an atom, is it the same thing anymore? You change it. You change what it is. You can't break up atoms if you want to keep the same thing. We started talking yesterday about the elements that are important in biology. And I gave you a little acronym that I told you was real important. And it was CHNOPS. CHNOPS. Those are the 6 most important elements in life. And they are: C is carbon. H is
hydrogen.
Yep. N nitrogen. O P is
Phosphorus.
and S is sulfur. Those 6 things are important in pretty much every living thing on Earth. And there is a lot of them in every living thing on Earth. Now, those are not the only ones, though, that are important in biology. We talked about a few other ones yesterday. Which one did we talk about that's important in your blood? Iron. It's important for you to be able to carry oxygen. And we talked about how the symbol for iron is Fe, which, unless you know why, it doesn't make any sense. We said that a lot of those symbols in the periodic table are coming from what language? Latin. And you'll see the same for a couple other ones that we mentioned yesterday. We talked about 2 that helped you generate electricity in your nerves. What were those 2? Yep. Na. What's Na? It's sodium. It's another Latin symbol. And K, that's potassium, also a Latin symbol. There are several other elements that we didn't talk about yesterday that are important in your body. Anybody know of another one? That's not an element. That's a compound, right? What would be another element that you need in your body?
Did we talk about like PU?
Oh, you don't want Pu in your body. That's plutonium. That's like that's what they make nuclear bombs out of. Don't think you want that. Yeah. Okay, we talked about iron already. What's another one? Yeah. Well, electrolytes are like sodium and potassium, so we got those covered. Let's look up at the periodic table. Turn around and take a look. Sodium's already up there.
No, it's not.
All right, so another one that you need some calcium. You need calcium specifically where? In your bones. You also need it for your nerves and muscles to work right. It's important in lots of places in your body. You need some zinc. You need some magnesium, for example. And there's several others. Chlorine, you need some chlorine. We're not going to go into all the ones you need. If you know these, you're in pretty good shape. The main thing is to know that little acronym. Those are the 6 most important elements in life. Know those. Now, I heard some confusion a second ago concerning these words down here. Let's make sure we know the difference between those words. An atom, again, is the smallest particle of a substance that keeps the properties of those substances. What's a molecule? It's 2 or more atoms that are what? Stuck together, bonded together. Something's holding them together. They become one thing. They're joined together. That's a molecule. And what's a compound? It's not necessarily a group of molecules. It's just a substance made of more than one way. More than one element, more than one kind of atom.
Like water.
Yeah, for example, water, H2O. H2O is a molecule, right? Because it's an oxygen atom and 2 hydrogen atoms put together, but it's also a what? It's a compound because it's made of more than one kind of atom. On the other hand, what are we breathing? Why are we breathing? Oxygen. So we make ATP and stuff, but we're breathing oxygen, right? What's the formula for that oxygen that we're breathing?
Okay.
It's O2. The gas in the air is not just O, it's O2. That's a molecule, right? 2 atoms connected together, but is it a compound?
Yeah, no. I mean,
It's only made of one kind of atom, right? Just oxygens. So it's a molecule, but also a element, because it's only made of one kind of atom. That's an important distinction. Compounds are made of at least 2 different kinds of elements. All right, if we talk about the word matter, it's a word you've all heard about before. In science, what does the word matter mean? Yeah, that's a lot of times you'll find it in a book, anything that takes up space. I just want you to think of matter as the stuff that we're all made out of. That's not a very scientific term. The stuff that we're all made out of. What are we talking about when we use the word stuff? Atoms, molecules, all the stuff that makes you up. Okay? But mostly we're talking about atoms and molecules. That's matter. The word mass gets used a lot in science. Mass is basically a measurement of how much what? How much stuff you're made out of. It's a measurement of how much stuff, how much matter. Now, let's think about this. Let's say you're an astronaut. You're on Earth. You've got a certain amount of matter, right? You go to the moon. Does that amount of mass change when you go to the moon?
No,
No, it is not. It's a weight change.
Yes.
You're still made out of the same amount of stuff, right? Your mass doesn't change when you move planets. But what does change? Your weight. Weight and mass aren't the same thing. Weight is a measure of how much what pulls on your mass. How much gravity. Okay? On Earth, there's a lot more gravity. Gravity is a lot stronger than it is on the moon, right? Anybody know about how much stronger gravity is on Earth than it is on the moon?
2/3.
So like 6 times stronger. So for example, if you weighed 60 pounds, if something weighed 60 pounds on Earth, it would only weigh about 10 pounds on the moon.
Dropping weight.
That's why when you watch video of the astronauts that were on the moon, they were like bouncing everywhere, right? Because it's easy to jump, because it's like they're almost weightless. Not quite weightless. But when they jump, they go way higher and way further on the moon because there's less gravity pulling them back down. Only about 1/6 of what's on Earth. Depends on how you measure it. A lot of times they measure it as 9.8 meters per second squared. But we'll get into that later. All right, let's move on down a little bit. Let's look up at the periodic table. Questions?
What is Fe again?
Iron. Let's everybody turn around and look at the periodic table again for a minute. In the periodic table, you have two numbers, okay, for every element. Let's just take, for example, carbon for a second. Let's find carbon. Carbon is element number 6, right? All right, let's write up here on the board what that entry for carbon looks like in the periodic table. We've got carbon, we've got a 6 up here, and we've got 12 point something down here. All right, those numbers on top, and in our periodic table, they're in blue. Anybody know what those numbers are called? They are called atomic numbers. Atomic numbers. That's different than atomic mass. What an atomic number tells you about an atom is what? What does it tell you?
How many protons?
Tells you how many protons it has in its nucleus. Now let's think about this for a second. Protons are what kind of particles? What's their charge? Positive charge. They're always found in the nucleus. If that number gets changed, what does that mean about your atom?
It's no longer.
It's not that atom anymore. It's something else. The number of protons determines what it is. So carbon is carbon because it has an atomic number of 6. If we added a proton to it, what would it be? It'd be 7, and it wouldn't be carbon anymore. It'd be what? It'd be nitrogen. Okay. Atomic numbers determine what element you're looking at. What other thing is usually the same as the atomic number? What other particle do you usually have the same amount of as protons? Electrons, because protons are positive, right? Electrons are negative. A neutral atom should have the same amount of both. But are atoms always neutral?
No.
They're not. And if they're not neutral, that means they either have more protons than electrons, or they may have more electrons than protons, right? And we'll talk about that in a minute. Protons are positively charged. Electrons are negatively charged. Now let's go down and talk about that bottom one. What's that bottom number called? Atomic mass, or sometimes it's called the mass number. What does that number tell you about your atom? Yeah, it tells you this. It tells you how many, it's talking about the nucleus. And it tells you how many protons plus how many what? Neutrons are in the nucleus. So it's protons plus neutrons. Now, normally we're going to round this off. So instead of calling it 12.011, let's just think of it as 12 for right now. We know that we've got 6 protons in the nucleus of this thing, right? This number right here, 12, is P plus N. So if we've got 6 P's, how many N's do we have? This is the number of protons. This is the protons plus the neutrons. We just subtract them, right? 12 minus 6. That tells us there's 6 neutrons. Now, let's take one where they're not the same, because they're not always the same. Let's look at maybe, let's look at bromine. Bromine, if you notice up there in our periodic table, there are 2 elements written up there that have blue symbols. Bromine and what's Hg?
Mercury.
Mercury. Anybody know why those 2 are written in blue? They're liquids at room temperature. They're both liquids at room temperature. Everything in black up there is what? It's a solid at room temperature. And the ones that are in red are what? Gases. Black means solid. White means man-made, artificial. So, look at bromine. If you look at bromine in your table, just wait a minute. Bromine in your table has these numbers. It's got 35 up top. And then down at the bottom, it's got 79.9. So I'm just going to call that 80 for right now. I'm going to round it off to 80. So that tells me a bromine atom has 35 what? What does that top number always tell you? Number of protons. 35 protons in the nucleus. And this number at the bottom is our number of protons plus neutrons. If I ask you how many neutrons are in this bromine atom, you're going to do what? You're going to go 80 minus 35, and you're going to get 45 neutrons. So to find the number of neutrons, it's the bottom number, the mass number, minus the atomic number. Bigger number minus smaller number. That's how you get your number of neutrons. Why are those elements, or those numbers at the bottom, decimals? Why are they not whole numbers? Notice most of those red numbers are decimals. How come? Is carbon, for example, is the bottom number in carbon always 12? No, sometimes, what's another form of carbon that you've heard of before, probably? No, just pure carbon. You guys heard of carbon 14 before? In carbon 14, this would be what the numbers are. Which means that carbon atom has how many neutrons? Big number minus small number. Guys, 14 minus 6. 8. 14 minus 6 is 8. Alright, what I'm telling you, those bottom numbers are averages. They're based on how common different forms of carbon are. Most carbon on Earth is carbon 12. But there's a little bit of carbon 14. There's a little bit of carbon that's carbon 13. And that's why those numbers up there are not whole numbers. They're averages. Let's go a little further. Yeah. Good question. See where LA and ACR 57 and 89, there's those stars there? Those two rows down at the bottom of the periodic table that are by themselves, they really ought to, the periodic table right here ought to be scooted apart. And then these two rows ought to be stuck right here. But the reason they put those two rows at the bottom is because if you did it that way, that would make the periodic table like as long as the wall. And it wouldn't fit anywhere. So they put those two rows at the bottom, and they're saying these two rows go there. Just to let you know. All right, let's go a little further here. One reminder about atoms. The protons and the neutrons in an atom are always going to be where? They're in the nucleus. That's what makes up the nucleus. And the electrons are sort of floating around on the outside, right? In something called an electron cloud. Why don't the electrons just keep on floating away and leave the atom? They're negative, and what's the nucleus? Positive, and what do positives do to negatives? They attract them, they kind of hold on to them. It's almost like gravity, right? It's almost like gravity pulling on a planet kind of thing. Can an atom lose some electrons?
Yes.
Yeah. Can it gain some electrons?
Yes.
Yeah. And if it does, what's going to happen to it?
It's unstable.
Not necessarily unstable, but it's going to change its way. If you gain or lose negatives, what's going to change about you? If you gain or lose negatives, what's going to change about you? You're going to become either positively charged or negatively charged, right? If you lose negatives, what do you become? You become positive. If you lose negatives, right? If you gain negatives, then you become negative. And what's the word for an atom that has done that? For an atom that's either gained negatives and become negative, or lost negatives and become positive? What's the word for those atoms? Nope. This is a word you'll see a lot in regular chemistry. Ions. Ions are atoms that are charged. And they're charged because they've either got extra electrons or they don't have enough electrons. One or the other. Ions. Charged atoms. Atoms with a charge. Yes.
If you were negatively charged, wouldn't you be like?
Not necessarily. You just attract the positive things. Yes. Technetium? It's really rare. It may exist on Earth, but they can't find it.
Where's it on?
So they made it in. It's a metal. No, it's a metal. Not a lot of uses that I know of. just one of those rare things on Earth. Yeah.
Okay, is that why like magnets they stick to metal because they're negatively charged? Or one of them-
No, magnetism's a whole different thing. Related, but different. All right, let's go a little further here. We're going to talk about two kinds of bonds. And you need to know the difference between these two things, and you need to focus with me for a minute so that you do know the difference. We're going to talk about covalent bonds, and what's the other one? Covalent and ionic. Let's talk about covalent first. Here's a list of things you need to know about covalent bonds. Remember, a bond is a kind of a force that holds two atoms together, right? First of all, covalent bonds occur between nonmetals. Let's turn around and look at the periodic table again for a minute. Most elements, are they metals or non-metals? Most elements are metals. And the dividing line on my periodic table is kind of starting to fade away a little bit. But if you guys look right in here, there's a little line that snakes up between boron and aluminum, between silicon and germanium, arsenic and antimony, and tellurium and polonium. This little line looks like a little stairway. Everything to the left of that line is what? A metal. Everything to the right is a non-metal. So really, just these things right in here, these are the only non-metals.
Number 80 can be
80? It's a metal.
Mercury.
It's a liquid metal. But it's a metal. Everything to the left is a metal. Everything to the right is a non-metal. One exception that I can think of, and that's hydrogen. Hydrogen's not a metal, right? It's a gas. And we'll talk later about why hydrogen is stuck over there. Hydrogen's kind of unique. It really ought to be in its own spot altogether. It doesn't really fit anywhere.
Is hydrogen not super flammable gas?
It is. Very flammable. Here's the thing. Covalent bonds. Covalent bonds occur between nonmetals. Let me get the door right quick. Yeah. You know, you gonna take it apart? All right. All right, so back to what I'm saying. And here's something you should have heard before, but let's make sure. Focus on me, not on them. Atoms sometimes are really reactive.
Like radioactive?
No, not radioactive, just react. But there's something that makes them not so reactive. In an atom, we've got the nucleus. Let's say this blue here is the nucleus. And then there's these little places around that atom called energy levels. Each one of these little energy levels can hold a different amount of electrons, right? And I'm not going to go into how many fit in each one. But when you get to the outermost level out here, let's say this is the outermost level for this atom. What are these electrons in the outermost level called? What kind of electrons? They're called valence electrons. Valence electrons. The ones in the outermost level. They turn out to be real important. Because if two atoms are going to react, what's got to happen before they can react? They got to bump into each other. And when they bump, what's going to bump first? The valence electrons. So those valence electrons determine how they react and what they'll react with and what they want, how reactive they are. And it turns out for an atom to be stable, meaning it's not reactive, there's kind of a magic number of electrons that need to be in this level. Anybody know what the magic number is?
12.
Nope.
6. 4.
8. Magic number is 8. Okay? For an atom to be stable, it needs to have 8 electrons in its outermost level. It needs to be stable. That's true for just about every element except the really tiny ones. What are the two smallest atoms in the periodic table?
Hydrogen and oxygen.
Hydrogen and helium. They only need how many to be stable? They only need 2. But the bigger ones, they need 8 to be stable.
Even the helium that's plutonium.
Yep. And they're still going to be radioactive. That's a whole different thing. But here's the thing. In covalent bonds, two atoms will share valence electrons so that they both get to 8. Let me give you an example. Let's say that we were trying to make chlorine gas. That would be a bad idea because chlorine gas is really, really toxic stuff and it'll kill you. Okay? Well, let's say we were making chlorine gas and we had 2 chlorine atoms. All right, 2 CLs. How do you know how many valence electrons are in an atom? How do you get it from the periodic table?
The atomic number.
No.
Atomic mass.
No. Everybody turn around and look at the periodic table for a minute.
The number that's on top.
Up top, you have those Roman numerals written in green. Those numbers up top will tell you the number of valence electrons. So find chlorine. Chlorine's element number 17, right? Cl. It's what's VII?
Oh, so 6, 7.
Don't worry about the A's. What's VII? 7. That means the chlorine atom has 7 valence electrons. But it needs how many to be stable?
8.
It's 8. You think if it has 7,
Anything over 10 is like.
well, let's think about it. 7 you think is going to be just a little reactive or crazy reactive? Crazy reactive. Because it's like, let's say somebody had you tied up and you had an eating week. They put a big juicy steak just in front of your face. Okay?
God.
Okay? And no matter how much you reach, you just can't quite get there. Okay? Your nose can touch it maybe, but you can't get your teeth on it. Okay? That makes you really, really want that steak, right? That's the way chlorine is. Chlorine's got 7 valence. It's almost to the magic number of what? 8, but not quite. So it's really, really reactive stuff. The most reactive elements in the periodic table are in group 7 and in group what?
8.
Nope. Group number 1, right over here on the left. Because here's the thing.
Oh yeah, 100.
Elements can get to 8 2 different ways. They can get extra ones, which is this chlorine's about to do. Or if they only had 1 in their outermost level, what can they do with that 1? They can give it away. And now the outermost level is the one below that, right? Which already has what in it? It already has 8. So if you give 1 away, then you drop back down to 8. So the 2 most reactive columns in the periodic table, column 1, column 7. If you took a hunk of sodium, for example, element 11,
Don't get that way.
and you threw it in water. We talked a little bit about this when we talked about the lab rules. It explodes violently.
Like pure
Okay?
sodium.
Pure sodium. Not like salt, pure sodium. Potassium, turns out as you go down over here on the left, the reactivity goes up. So if you took potassium and you threw it in water, it's not going to only explode, it's going to also make this big fireball. And rubidium would be worse, and cesium would be worse. Anyway, back to what I'm saying. In a covalent bond, atoms share these electrons to get to 8. So chlorine's got 7. Chlorine atom starts off with 7. So we show the electrons as dots. And we usually write them in pairs like this. So that chlorine's got 7 to begin with, all right? I'll get you in a minute. It's really reactive. This chlorine over here also has 7. It's really reactive. They bump into each other. What happens when they bump into each other?
No. They clear that up.
They're saying, hey, I want you to think of covalent bonds sort of like communism. Communism. Now, communism in theory is a good thing. Okay? I hate communism because it never works. But in theory, what's the idea behind communism? In theory, is everybody is equal and everybody's going to share everything equally. And if we all would go get a job and we would all work and we were all equally responsible, that would be great, right? But are we all equally responsible and equally going to work? It never works, okay? You have people who aren't going to do anything, okay? You have others who are going to work hard. So communism never works, no matter what they try. But let's think about the idea. Focus on it. The idea is this, that you share to become equal. In this case, these atoms are trying to share to become what? What are they trying to become by sharing electrons? What What did we say 8 was the magic number for?
Oh, they're trying to become
Stable, unreactive. So here's what happens. This electron from right here and this one right here, they move out in the middle. This atom right here uses 2, 4, 6, 8. It's good to go. This atom right here uses 2, 4, 6, 8. It's good to go. This area right in here, that's the bind. It's a pair of shared electrons. What do we call a diagram like that? Where you probably did this in different classes, where you have two circles that overlap. And it's called a Venn diagram, right? V-E-N-N. And what's the middle, where the circles overlap? What does that mean about the two circles? Shared properties, right? Same thing here. It's a Venn diagram. And these two electrons in the middle, that's what they're sharing. That's the bind. And now what can we say about these two chlorine atoms? They're stable. They're not reactive anymore. They're not dangerous, at least not in terms of reacting with things. Still poisonous, but not so reactive.
If you were eating chlorine, would you die?
If you breathe it, you would die. Yeah.
So like if you
Go ahead. You had a question a long time ago.
Chlorine, if it's a gas, then how do you use it for?
they make it.
They don't use it in gas form. They either use it in a salt form, which is not a gas.
It was like salt.
They connect with something else.
So my question was, if you eat that chlorine, will you die?
It's pretty, yeah, well,
That's why salt kills you. Just take the brick.
enough of it, yes. Anyway, back to what I'm saying. I'm going to wait on everybody to focus with me. So in covalent bonds, non-metal atoms share electrons. They're sharing them to try to get up to 8. Ladies. When you have a particle that's held together by covalent bonds, we call it a molecule. So the word molecule only applies to things that are held together with covalent bonds, which means molecules have to be what kinds of atoms? What kinds of atoms make covalent bonds? Read the PowerPoint. What kinds of atoms make covalent bonds? Non-metal ones. Okay. So when we're talking about molecules, we're talking about compounds formed by non-metal atoms. Can't be any metals in them. The molecules have no overall charge because nothing's doing what here? Nothing's gaining electrons or losing electrons. It's just what? Sharing. So there's no overall charge. There's positives and there's negatives, but they're equal, right? So the overall charge of molecules is the same. Now, one thing that confuses that a little bit is this idea of polarity. When we say a magnet has poles on it, what do we mean?
It has
It has two sides that are opposite, right? It's a north and a south. That's what poles mean. So if we talk about a molecule that's polar, it has two sides that are oppositely what? Charged. Hold that thought for just a second. Hey. I can, I've already been doing it. Are they going to just going to send down the ones that are interested? How? Okay. All right, back to what I was saying. A molecule that's polar has a negative side and a positive side. And the most common molecule out there that you need to know of, that you need to associate polarity with, is water. Water is polar. And let's think about why. Let me make a little space up here. Actually, let me go to another slide here. I'll just do it on this one. All right, here's an oxygen atom. An oxygen atom has how many valence electrons? All right, rally here right there.
No.
8.
What is it? VI.
7.
VI. 6. 6. I know. Other people were saying something else. So we're going to draw 6 dots around the oxygen. It doesn't matter where you put the dots for right now. All right, that's connected to 2 hydrogens, right? H2O, water. How many valence electrons does a hydrogen atom have? 5 hydrogens. It's in column 1. It's got 1. I'm going to draw one of the hydrogens over here. Here's its electron. I'm going to draw one over here. Here's its electron. Now, we already said that most atoms need how many valence electrons to be stable? 8. So the little ones, like hydrogen, only need 2. So here's what happens. This hydrogen bumps into this oxygen. They share these 2 electrons right here. So we got 1 electron from oxygen, 1 electron from hydrogen. That makes a bond. Same thing happens over here on the other side. 1 from oxygen, 1 from hydrogen. Those get shared. And the oxygen is using all 8 of those. So it's got 2, 4, 6, 8. Each hydrogen has 2. So again, all right, that's why. Now here's the thing though. And this is the part to understand. Water actually looks more like this. The hydrogens are on one side and the oxygens are on the other. And if you look at this picture, you'll notice that these shared electrons I drew closer to which one of those atoms? Closer to the oxygens or closer to the hydrogens? Closer to the oxygens. They're sharing them, but it's kind of like one of those deals where you say, Michael and I are going to share some candy. So I give 1 to Michael, and 2 to me, and 1 to Michael, and 2 to me, and 1 to Michael. You know, they're sharing, but they're not really sharing how? Equally. Okay. So the negatives. Remember, slow down. Remember, electrons are negative. The negatives are a little bit closer to oxygen than they are to hydrogen, which means that this side of the water molecule has a negative charge, and this side has a positive charge. And that's what we mean by polar. If 2 water molecules get close to each other, what happens when another water molecule gets up next to that one? They stick. Because what happens to positives and negatives? They attract each other. So there's a force between the molecules. Well, if another water came up here like this, since the hydrogens are positive, there's a force between those 2 molecules. And we'll end with this today. What's it called when 2 things that are alike stick together?
No.
2 things that are alike stick together. It's called cohesion. Okay? Water is cohesive. It sticks together. Let me say this, and then you can pack up. Well, then, listen to this. We'll be using microscope slides here before too long. With little glass slides. If those glass slides get wet and they're stacked up, they are really hard to get apart. And the reason they're really hard to get apart is what's happening. The water is acting like glue. Okay? The water is attracted to both sides and it's attracted to the water in the middle. It's acting almost like glue. They're stuck together. All right, I'm going to stop there. Let me turn off our recording.